How dare they? Okay. I know, it's my middle name, so I've suffered that my whole life. Strong acids and bases completely dissociate in solutions. All right, so if we have what we're going to call Ka, why am I going to call it Ka? Because it's for an acid. If I have Ka for the dissociation of HCl goes to H plus Cl minus, how would I write this? And all of you disliked, not all of you, but tons of you like, what do you mean by the mass action expression? I thought I reviewed that a lot. That's where you write it out with the symbols. What would this look like?
The concentration of
Oops. Okay.
Divided by the concentration of hydrochloric acid.
All right. Thank you. So that would be the mass action expression. It's just the thing written with no numbers in it. Okay. Now, thank you, Nisha, for never once being distracted and talking when you shouldn't. I appreciate it. Okay. Now, look. What does this sentence say right here? All right, so strong acids and bases completely dissociate in solution. So let's think about this. Ka would be H plus over, or sorry, times Cl minus times what number, or divided by what number? 0. So one thing you should know about strong acids and bases, and strong only, not all of them, strong, is there is no Ka. We don't worry about it. That number's almost 0. So that number is gigantically large, and we will not find K values for strong acids and bases.
Wait, so for what? No, I was saying
the concentration of this, since this completely dissociates, then there is no HCl. So for strong acids or bases, we do not calculate Ka or Kb. You awake today? Okay. Do you kind of understand why again?
Yeah.
They completely break apart. So that's like a 0. All right, now here's what's kind of cool. And I'm going out of order, but I just feel like doing it anyway. Here we go. Weak acids, and this works for bases, only partially. 2 L's and partially, I think so, right? Dissociate in solution. All right. So if I have, well, why did I do that? I changed what I was going to write, but that line would have worked for both. If I have acetic acid, HC2H3O2, and it dissociates into H plus C2H3O2 minus, what would my mass action expression look like? Okay, oh, never moving that again. Okay. Oh my, I miss my slate so bad. It just stops talking, like the USB, the wireless thing's not working. Oh, it's charged. It'll work for like 2 minutes. None. Don't memorize a single weak one. Memorize the 7 strong ones. 7 strongs, there's 10 million weaks. So memorize the 7 strongs and then go from there. Say that, start the sentence over again. No, they would not. They'd be the conjugate base of a weak acid. Like this piece right here. And this piece right here, my acid, my conjugate base. What that means is, oh, I hate when that happens. If I touch the screen and my body touches that corner, it shocks the crap out of you because I'm on this like constant electrifying surface here. So your answer, like there's those words, they go together, but that's not the reason why.
So,
Okay. Oh, go ahead.
a weak acid will have a strong conjugate base.
No,
Oh,
because it would come the other direction.
Conjugate will never be. Will the conjugate never be strong?
Yeah, it can be. We'll get there, but let's.
If you dissociate, that means
Well,
the conjugate base can take on H plus.
okay. Yes, sir. Hold on.
I'm admittedly a complete technological moron. I just shared you the link. Is that what you needed?
That's what I need. I'll do it. Check with me at the end of the hour. Make sure I did it. Okay. For right now, I don't want to go back and talk about that. We can, but I want this to make sense. So give me this for a minute and then we'll see what happens here. So this Ka would be equal to that value. Since this is a weak acid, most of this does not dissociate. Only a little bit will. You okay with that? So this is a small number. Or sorry, this is a big number. These are small numbers. But here's what's cool about Kas. If you think about the value of H plus and the value of the acetate, what do you know about them? This is a big K. No, this is a small K. Sorry.
the other one will be a big K though.
Right. This is a big number. Those are small numbers. But that's not what I'm looking for. There's a actual thing that we can know about both of these. They're the same. Good job.
Hey.
They're the same. Because look, for every one of these that breaks apart, how many of these are there? And how many of these? One. Sort of with me? So if these are the same and I don't know them, I can call them X.
Oh, I see.
This is where that one pump came from.
This is where it gets way easy actually, but yes, it's the same idea. So my Ka is really X squared over this concentration. Whatever, it's that. You with me? Okay, now here's something that's kind of cool too. Most of this does not dissociate. So let's say I had a concentration like originally of 0.5. If we did a little math, which we won't need to do, but it'd be something like 0.0001 of it does break apart. So yeah, so what's this minus that? What can we say about these two numbers? They're basically the same number. So if I take x squared and divide it by 0.5, or x squared divided by 4.4999, the difference in my answer is not going to be very much, right? So this is what's really cool about the Ka of a weak acid. The Ka for a weak acid will always be, as long as it's monoprotic. What I mean by monoprotic is the following. If it's like HCl, monoprotic, H2 SO4 diproduct. And that matters because then we'd have 2H plus 1 SO4 minus. So then we'd have an exponent, and that's where it gets weird. But we don't do diproducts very often, so just come back here. As long as we have monoprotic weak acids, Ka is always equal to X squared, which remember, X means the concentration of H plus. So Rollins, no, not Rollins. Okay. So it means the concentration of H plus or whatever the anion was, you with me, over the initial concentration. And that makes our K values really, really easy to calculate. And here's what's kind of cool. It's where we're kind of going next. If I know X, if I solve this, it is solving for the concentration of H plus, right? This is really cool. And I'm going out of order, but it's just kind of cool. The concentration of H plus, if I take the negative log of the concentration of H plus, that'll give me the pH. So I can give you the pH and find the K value, or I can give you K and I can find the pH. They're all tied together. Now here's what's cool. If I can find the pH, I can find the Ka. That means I can find the Kb, which means I can find the concentration of hydroxide as well.
So is there an equation that relates to you?
Not a direct one, but indirectly, and we'll learn them. So weak acids, pretty cool. We'll do a ton with them. Strong acids, we almost do nothing with.
Because it's so
So is their concentration of stuff, like their H plus is equal to whatever you started with. They're completely ionizing. All right, let me do this for Colomar real quick. Don't go too crazy. Hold on. Okay. Tolman asked me, is there a million weak acids to memorize? The answer was no. There's 7 strong. And honestly, we went over it first try, chapter 4. Same things we learned before. Yeah, well, okay. No, maybe you didn't learn them. Should you have? Yes. So HCl, H2SO4, HBr, HNO3, HClO3, HClO4, and HI, because they're the ones that dissociate the best.
like because they're like
It means their conjugate bases are not strong enough to stick to an H.
yeah.
All right.
Why can't you buy hydrofluoric acid?
Hydrofluoric,
Yeah, hydrofluoric.
it's dangerous. Like if it's stored at Ace Hardware and it falls on the ground, it eats a hole in the ground and eats the skin off of everyone's legs it lands on.
Doesn't it not melt through plastic though? Like certain types of plastic?
PVC, it does not react with PVC. All right, but you can get HCl. They sell this at Ace Hardware.
Figure.
It's called Muriatic Acid. I wouldn't buy it. The same I buy, the 12. You don't want to buy that. Like you open the lid and inhale, you will hurt your lungs immediately. So just be careful. Like it even says on the label, don't transport. You're like, wait a minute, how do I get it out of Ace Hardware?
Burn your skin.
Absolutely, it burns your skin. Okay, moving on.
What did I do? Take the list away.
So follow this. In any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So this is the real answer to Reese's question. So when we have HCl reacting with water, we end up with our acid, my base, my conjugate acid, and my conjugate base. Since this happens right here, H2O, water, is a much stronger base than Cl minus, so the equilibrium lies so far to the right, K is not measured. So what we're saying is water can hold on to the H plus. I don't know what I just did right there. It can hold on to that stronger than Cl minus can. If water wins, then we have a strong
But
substance.
Cl minus is more than the part.
So water can separate those two here, hence why it's a stronger base.
The proton will move towards the water. The H plus will move towards the water.
Yeah.
But the charge of Cl minus is a lot higher than the dipole.
So
Why wouldn't I go?
that's a valid question. If you think about what Cl minus has done though, it wants an electron, right? Cl wants an electron. Cl minus has an electron. It doesn't care who it's with anymore. It took the proton from, sorry, it took the electron from hydrogen, and now that proton's free to do whatever it wants. Cl minus is completely harmless and non-reactive. Cl was. That's why it removed the electron, but then it doesn't care about the rest. Does that help at all?
So would this create an ionic bond?
No, not really. No,
Not any attraction?
no, there's attractions, but no. Go.
And that's why it can't go have a reverse reaction, right?
Right, because there's no desire of it to reform with H and share. It took. Why share if I've already taken? There's no advantage to go back the other way. Yeah. Yep. For sure. You can eliminate the water. Once it's gone, then all you're left with is H and Cl. Yes.
Okay, so if you're just looking straight at the equation, then what are you looking for to know what is the strongest base out of all of them?
You need to memorize the strong bases.
So you just find the strong base and then you just know that, like, you know, the H2O is just
Yep.
stronger than C.
Now, yeah, well, and the easiest is to memorize both the strong acid list and the strong base, and then realize their conjugates must not be able to come back the other direction.
So basically.
Because trying to memorize it the other way around is a list that's that long. Go, quick. Probably. All right.
So if it completely dissociates, then water is the stronger.
Yes. Okay, then weak. Acetate here is the stronger base than water, so the equilibrium favors the left side. So what that means is that this acetate is more attracted to a hydronium ion than water was, so it will go towards the reactants.
So it's saying the reverse reaction is favored.
Correct.
when it says
Which means we have a weak acid. All right, so acetate, whatever, sorry. So the equilibrium favors the left side. K would be less than 1. Question? Oh, just pointing. Very good. Okay, now, autoionization of water. As we have seen, water is amphoteric. Yeah, I've never seen that before, except for 2 days ago. What did that mean? No,
except for donate.
it can go either way. It can give an H away or it can take an H. All right? So amphoteric. It means it can give off an H or it can accept an H. It can become OH minus or it can become H3O plus. It can go either way. So in pure water, a few molecules act as bases and a few act as acids. And that makes sense. It turns out they're going to be the same value. If I have just as many acting like an acid, that's really hard. I I will have just as many acting like a base. If they're equal, I don't really have either one, right? They cancel each other out. So we have something that's neutral. All right, this is, I'll tell you in a minute. This is referred to as autoionization. So autoionization is when two water molecules collide to form H3O and OH minus. And I'll show you in a second. Go ahead.
That's why on that scale you were showing as application of like water, that's a lot of water.
Yep.
That's what I was trying to explain, but I didn't.
Okay, sorry, I didn't understand your question.
Wait, what?
Okay, so this is what happens.
Call you an idiot.
Shh, don't fight, don't fight, don't fight. We have O, H, and H. This is water, right? Also known as H2O. It's polar, so we know hydrogen's positive, positive, and the oxygen's slightly negative. We know those things, right? If I take another and they come by each other, I feel like I hit that a few times. Okay, now, if I, oh, that was stupid. I always do that. That's fine. Don't worry. Okay, so here's another water molecule, and it's flying along, and you have the H plus here, and they're constantly colliding because everything has some energy because it has temperature, right? All right, so water comes along, and these O negative and H plus collide. Occasionally, for a very short period of time, this H will be more attracted to these lone electron pairs right here than its own O. Now, I gotta be careful. This is not a hydrogen bond attraction. This is a chemical bond attraction. So for a moment in time, this reaction, or sorry, oh, that was a lot bigger than I thought it would be. This bond, right? Okay, that was the wrong way, Tom. That one. Okay. So what happens is they form a bond. And now I'm left with H3O and OH minus. Now, they don't like to be that way. So it will flip back pretty soon. Go ahead.
So how is it, well, I know there's a difference between chemical bonding and hydrogen bonding, so like what makes it different?
A transfer of electrons. So it's really this pair of electrons ends up kind of over here, and then they move completely. It's a little tricky, but there's not a whole lot of difference. But okay, anyway, so the autoionization is when these collide and they form H3O and they form OH minus. This is an acid, that's a base, but in pure water, the amount of them are always equal, so it's still just neutral.
So this is only temporary.
Yep, but it's million, there's like, I mean, I don't know how many zeros we would add, 23 of them for 18 grams. There's so many atoms going in that they're constantly flipping back and forth. But if it's neutral, pure water, we know that they're both equal. That's why it is neutral.
So the left side is still safe.
Absolutely, like by a lot, like 7 zeros.
Yeah.
All right, so now this is an equilibrium thing, so we can kind of mess with it. So what we have now is a little bit of math. Oh, that thing's right there. How about I just go right here? All right. The equilibrium for this expression would be H3O plus OH minus, and we would divide it by water, but we really wouldn't. How come? Oh,
Because it's water,
It's
it's
completely
temporary.
Okay.
no,
It's not because it's a fraction.
closer. It's what?
It's the solution.
No.
Because it's done. It's all-
No.
A fraction.
No. No. Why is water not in the denominator?
Because it is water.
No, because liquids and solids are not included.
Right.
That's why, peeps.
Wait, so that's a gas, let's say?
No,
Is an oxygen ion.
these are aqueous. It doesn't matter how you pronounce it. It doesn't matter. Moving on. I'm going to shoot myself, but right after I take all of you with me. All right, here we go. That was a little violent. I'll have to edit this video too now. All right, this special equilibrium constant is referred to as the ion product constant, or KW.
So can this be transferred to any equation that's similar to this? or
No,
just
this
for
is
water?
only for water, and that's why it gets its own KW. It means the equilibrium expression for water, and it's always the same. It is H plus times OH minus. And what's really nice is we already know the value of KW. So that's really convenient.
Because it's consistent throughout every-
Yep, it's always 1 times 10 to the negative 14. So, well, no, it's at 25. And we'll never change the temperature on that. All right, so what's cool about this is since I know, I don't really do that, whatever. Since I know this is always this value, if I can find one of these, I can always find the other one. Really simple math. You take 1 times 10 to the negative 14 and divide it by your given. So this is actually like the third and fourth way we can find the same things I talked about a little while ago. If I have even one piece of information, I can put this whole puzzle together, and it will come together. Not today. I know some of you are like, what the?
So you'll always.
It all
be
comes
given
together.
the B pluses and always minus.
For this type of problem, sort of. You may not be given that, but you might be given the Ka. And if you have the Ka in the initial, you can solve for that. You might be given the pH, but if you have the pH, you can find the H plus. Like everything's 100% related in these problems. What did you say, Gabe? Yeah, there's the log. All right, so it's really pretty cool, but kind of gets tricky here. Okay, so here is a summary of a lot of stuff we're going to work on in the next few days. So pH, these are all equations that are given to you, or you should be able to figure out. pH is equal to the negative log of the H plus concentration. P means negative H, or sorry, negative log. H means hydronium. So just the P and the H is telling you that math equation. That will be either given to you or you can solve for it. There's the POH, which we don't use all that often, but the POH is the negative log of the OH concentration. Then we have what we call the pKa, and the pKa is the negative log of Ka. We have pKb. You could probably guess it's the negative log of Kb. pKw, this is fun. All right, that's the negative log of Kw. All right, now, all these are related to each other. Anytime you see a P, it means negative log. Log is always just finding the exponent, 10 is raised to, that gave you the answer. So if I have like 1 times 10 to the negative 7 as my H plus concentration, if I took the negative log of this number, its job is to find the value 10 is raised to, which is negative 7, right? But that's a negative of negative 7. So this would be a 7.
It's a positive seven.
It's a
The
positive.
log is always negative.
Well, I have a negative log here.
Yeah, and
The exponent is always negative. So this would be the pH. And pHs are always equal to positive values. Okay. I promise it'll all click.
We don't even have to come to the log, do the calculator. We can just go.
Well, most of the time you will. That only works if this is a 1. If this was like a 3.1, then you got to type it in.
Like, concentration of color.
Molarity or molars is fine. Okay, now pH. We've talked about it. We've talked about it in a different chapter a tiny bit. We've just like had it in problems that didn't really matter, but now it's time to get after it. pH is defined as the negative base 10 logarithm of the hydronium ion concentration. The negative. All right. And once again, that's so that pH will be a positive value. Does that make any sense? Now, we don't usually, the base 10 is kind of redundant because if it just says log, log is to the base 10. So I don't really need to add both of those. All right, so I can plug these in if I'm given a real value of the constant, not real. If it's not just a 1, I use my calculator. So 2.8 times 10 to the negative third, if that was my H plus concentration, I just type that into my calculator. Yeah, so I turn it on. I hit negative log 2.8 times 10 to the negative 3, and I hit enter, and I get 2.55 is my pH. You're doing that problem wrong. Just doing it wrong. Someone else ask a question?
So you still put in the 10 to the negative 3.
Yes, you type that all in. So pH, if you're given H plus, is super simple. It's just typing. Okay, let's talk about the reverse. I don't have a slide on this, but you need to know how to go both ways.
Is there reverse pH?
Yeah. If I'll show you. No. Here we go. If I know the pH is 6.5, but I want to know the concentration of H plus, I just take the inverse log. And if you type, not E, it's log, that's for ln. If you hit inverse log, it's just 10 raised to a number. Then I take the negative value and put the pH. And that would tell me my concentration is equal to, you already typed it out, 3.16 times negative what? So I can go either from pH to H plus or H plus to pH.
Oh,
And we'll call that good for the day. What?
It's not just H plus, right?
It's technically H3O
No,
plus.
anything could be in the correct. It can be the concentration.
No.
it's just
If I'm talking pH, this must be H. Now, if I wanted to find the P of K, like potassium, I could do that, but that's not something we ever do. I knew she was tired. I could sense it. All right, we're done. That was a lot. Tomorrow we'll do problems that put it all together. They're kind of fun, but I'm kind of weird, so maybe they're not that fun. Garrett, it was good to see your name online.